Hi everyone, and welcome back to part 2 of lesson 1. Thanks for coming to this new video. And when we left off on that last video, we were talking about how we can change all these values of x's to result in the value of y. And we found out that we can take the value of x and subtract it by 3, and that's going to give us the value of y. And it works for every situation. So we can do 3 take away 3 is 0, 2 take away 3 is -1, 4 take away 3 is 1, and x take away 3 is always going to result in y. So that's how we can get this equation here, y equals x take away 3. All right, so we're going to jump back to Pearson here, move on to part 2. And here we're talking about the differences between what we call linear functions and nonlinear functions. So every time you have a line that's on a graph, it's either going to be linear or not linear. And there's certain rules that we can look at that are going to result in linear or nonlinear functions. So we're going to take a look at both of these lists, and actually I want you to take a look at them and see if you can tell me if you notice anything that's on this nonlinear side that you don't see on the linear side, or vice versa. See if you can figure out why these 3 equations are over here and these 4 equations are over here. All right, hopefully you had some time to look at that. And maybe you noticed there's a few things that are different about these equations that you don't see over here. For example, there's an absolute value sign. So we see that there's an absolute value of x. And I'm going to go back to Desmos here. And I've actually programmed these in already so we can take a look at them. So y equals x is my green line. That's just a standard y equals x line. And then I'm going to put this y equals absolute value of x line on. So you can see here it's this purple line. It follows the green line exactly. It's exactly on top of this green line until it gets to the origin, and then it shoots off over here. So is the purple line a straight line? No, it's a combination of 2 different straight lines, but it itself is not a perfectly straight line. It's the shape of a V. And the reason it's the shape of a V is because if you have absolute value, the absolute value means the positive value of a number. It's the distance from 0. So we couldn't ever have a negative value for y, because even if I put in -6 for x, I need the absolute value of -6, which would be a +6. So that's why we have this V-shaped line. So that is not a linear function. Then let's take a look at the next one, which I don't think was y. Let me take a look. It was a equals s squared. So that's the formula for an area of a square, but I'm actually going to change it to y equals x squared. When I turn that one on for you here, it's in black, you'll see that it's the shape of a U. So it's a curved line, which is called a parabola. And if this happens anytime we have the x value squared, so it doesn't matter if we have a 3 in front of it or a -10 in front of it. If we have a negative number, look, it actually goes down to the other 2 quadrants. But we have this U-shaped item on the screen. And if this was not squared, if it was in a third, raised to the third, it would be this kind of squiggly line here. If it was a fourth, it'd be back to this U. If it's a fifth here, 6. So if you notice, anytime it's raised to an exponent, if it's an even exponent, it's shaped like a U. If it's an odd exponent, it's shaped kind of like a squiggly line. So anytime you have an x with an exponent, it is not a linear function. All right. And then this last one is y equals 5 divided by x. This one's kind of a crazy one. Turn this one off, turn this one on. Here we have that one in red. So it's these 2 lines that are both curved, and they are kind of mirroring each other. They're shooting away from the origin. So let me zoom out a little bit and I can show you. So here they are right here. And those are obviously not straight lines, so those are not linear as well. Okay, so now let's jump on to, actually I'm going to turn these all on so you can see them again if you need to. And then we're going to jump into the linear rules just to see kind of what these ones look like. So b equals 7 minus a. So I'm going to change it again to y equals 7 minus x, because that's the language Desmos understands. Take off all these not straight lines here. There we go. So y equals 7 minus x, that's a straight line. X, or y equals 3x. Let's try that one. Y equals 3x. Yep, another straight line. So these are all going to be linear functions because they all result in straight lines. And here we have two that are really similar. So y equals x divided by 2. So y equals x divided by 2. You get a straight line. Let me turn these ones off. But if I have y equals 5 divided by x, I get that red line, remember? So the difference is you cannot divide by x. This one is divided by x. This one's divided by 2, or that's the same thing as multiplying by 1/2. So you cannot divide by x to have a linear function. So you just have to memorize that little rule. And then we're going to jump into this quick example together. So we need to determine if each rule is linear or nonlinear. So I'm going to start here. I notice that the x is squared, so I automatically know that it's nonlinear. Here the x is not squared and it's not being divided, so that's linear. Doesn't matter that this is negative, as long as there's no exponent here, that's going to be linear. Here we're dividing by x, so as soon as we see we're dividing by x, we know it's nonlinear. And here there's nothing going on, no absolute value, no exponents, so we know that that's going to be linear as well. All right, now I want you to take a look at your Got It and see if you can tell me which one or which ones of these equations are linear functions. All right, so hopefully you had some time to take a look. If you need more time, feel free to pause the video. And hopefully you said it was options 1 and 3, because 1 is being divided by 2, that's totally fine, and 3 does not have any exponents, so that's okay as well. And then 2 is not a linear function because it's being divided by x. It's that tricky one. Okay, we're going to skip the second Got It here and briefly go through this key concept. Here we're talking about a dog walker who's earning some money. And the dog walker is earning $10 plus $3 per dog. So we're asked to figure out, like if we're trying to figure out how much money she's making, we need to know how many dogs are being walked, and then we'll be able to tell how much money. So here they put in 2, oh, I'm sorry, now they're putting in 3, and they're getting 19. So let's walk through how they got that. They're putting in 3. What do I mean by that? Well, that means that we're using this situation and we're saying, okay, a dog walker is earning $10 plus $3 per dog. If she's walking 3 dogs, we would do 3 times 3 is 9, and 10 plus 9 is 19. So we put in a number of dogs and we got out $19. That's because she's going to make $19 for this walk. Before, it went a little quickly, but maybe you saw that a 2 went in. Let's figure out what it would be for 2. So if there were 2 dogs being walked, it's $3 per dog. Anytime you see per, that means multiplication. So you're doing 3 times 2 is 6, and then 10 plus 6 is 16. So that would have been a 16 here. Okay, and we can use this information to write a rule. And they said that they're using D and M for money. So the rule would be, I'll squeeze it in somewhere up here, the money equals $10 plus $3 per dog, and they're using D for dog. So plus 3 times the dogs. And that would result in our rule that's being followed for this function machine. All right, so M equals 10 plus 3D. So we can put in any input here and get the amount that she would earn. So if she was walking 100 dogs, we could put in 100 for D. We do 3 times 100 is 300, plus 10 is 310. She would earn $310. All right, so I actually already put this example here on our whiteboard. And I need to erase my previous work from a different class. Just a minute. Okay, so I'm looking at this problem that says a swimmer burns 8.8 calories per minute while swimming laps. Which function rule describes how many calories C the swimmer burns during any number of minutes? Okay, so this problem is telling you, hey, when we're talking from now on, we're going to use the letter C for calories and the letter M for minutes. So I'm going to say C equals calories. Oh, calories burned. Oops, I'm running out of room. Burned, we'll just know that that means burned. And M equals minutes. So I'm defining my variables. I'm saying, okay, from now on, I'm not going to say calories burned in minutes. I'm going to say C and M. Okay, so this person is burning 8.8 calories per minute. Oh, there's that word per again. Per means multiply. So we're going to say 8.8 times what? It's 8.8 per minute. So instead of using any other letter, we're going to say M for minutes because we just defined that. And we're going to say, well, that's how many calories she's burning. So she's burning 8.8 calories, or 8.8 calories per minute will result in the calories burned. So if she swam for 10 minutes, I could draw my little input-output machine here. This is a silly looking machine, but here we go. Give it some depth back here. All right, so here's my input. I would put a 10 in here. My rule is to do 8.8 times my input. So my input here is M and my output is C. So I would do 8.8 times 10, which would be 88 calories burned. So 10 minutes of swimming equals 88 calories burned. And I could keep doing this. If I did 100 minutes, it would be 880. If I did 50, it would be 440. So I can always put in any number into my input and get a new number out of my output using the rule that I generated from the sentence. Okay, here's our got it. That's in your book. It says, Matt is 3.5 years older than Sam. What function rule describes Matt's age during any given year? So we're looking for Matt's age. So we're looking for what is Matt's age. So our final equation is going to be M equals something. And Matt is 3.5 years older than Sam. So Matt is 3.5 years older than Sam. And so I used M for Matt and S for Sam, and I got my equation. All right, so this is just practicing us reading the situations and being able to generate an equation from the situation. Okay, let's jump into our close and check for today. And find your companion page. On this page, I want you to do numbers 1 through 3. But I really just want to make sure that you can get 2 and 3 correct. I want you to try number 1, but I want you to focus on getting numbers 2 and 3 correct. We'll be practicing more with number 1 in the future, but just focus on 2 and 3 and then coming back to check your work. All right, if you need more time working on your own, please pause that video now and then take a look at numbers 1 through 3. Pause the video to grade your work, make any corrections, and then I will see you very shortly for lesson 2.